Hi, everyone. Okay, so this is the next episode in our continuing discussions with interesting folk. And today we have Lee Smolin, who is a physicist who I have known off and on for a very long time and works primarily at the Perimeter Institute and University of Waterloo. So let's see. So Lee, I think we probably first met probably around 1980, sometime like that, maybe 40 something years ago. And
Yeah.
so what were you, at that point, I remember you were doing all kinds of physics I didn't understand and a certain amount of artistic type stuff, as I recall. What were you working on back in those days?
I don't remember anything artistic, although I have done artistic stuff since. I was working on quantum gravity. I've always been working on quantum gravity.
So how did you get into quantum gravity?
It's the same way I got into physics. I was first interested in architecture. And so since I was a little bit ahead in math, I wanted to build buildings which were generalizations of geodesic domes in which I could take arbitrary curved surfaces and build a structure out of them. So I knew a little differential geometry, and I developed a program to triangulate a sort of general curved surface that I would give it a formula for. And I was a high school dropout, so I was sort of playing around with those kinds of stuff. I was very influenced by some of the architects around that time. And there's one guy whose name I'm not remembering, but I'm sure you'll know, Buckminster Fuller.
Sure. Did you meet him? Did you meet him?
Yes, I met him a few times. And so I was using the public library, and one day I
Where did you grow up?
This was in Cincinnati, Ohio.
Okay.
And there was a shelf I had been taking physics books home, general relativity and so forth. But to learn the differential geometry to do the structural calculations. And I noticed that there were a lot of chapters on general relativity. So I got interested. And one day I took home a book of essays about Einstein, edited by Schlipp. You probably know him. Albert Einstein, philosopher, scientist.
Yeah.
And it had an essay by Einstein called Autobiographical Notes. And I just read that in one sitting, basically, one evening. And it said, something went off, and a little voice came and said, I could do that. Now, I had never taken a physics class. I was a high school dropout. I had, for those days, some computer skills, but only nothing compared to what people that age have.
So when you were writing something to triangulate surfaces, was that like a Fortran program or something?
It was.
And so Buckminster Fuller was very big on this whole tensegrity, this sort of structures meet geometry. Was that the kind of thing you were into, or is it more the pure geometrical, how do you take the surface and make it discrete type thing? Boy, this is I didn't know when I asked this question, I had no idea what the answer would be. And this wasn't one of the answers I was expecting. So that's really, really cool. Okay.
Well, I only understood much later when I was interviewed by a journalist, Dennis Overby. And he said, you're doing now in quantum gravity exactly what you were doing when you were a high school dropout with architecture. And in a way, it's true. Anyway, I really got a mission from Einstein. Einstein was very clear that physics was in not a very good state, and there was quantum mechanics, which he didn't believe, and he felt we need to complete it with a better theory, and there was a relationship between physics and space and time and quantum physics. So in that evening, I got a kind of mission, because I'm talented at some level, but I'm not deeply, deeply talented as a mathematician. But somehow I got this strong sense I could do that, with knowing nobody who did it.
Right. Well, Einstein always used to say that he was very challenged as a mathematician. I know exactly what he feels like, because as you try and build these theories, and it turns out you need to wheel in all kinds of fancy mathematics, it's a different level. But so that essay must have been written by Einstein in like the early 50s, maybe?
Yes.
And then you must have been reading it sometime in the 70s.
Exactly, early 70s.
But so that was a time when, in physics, particle physics was getting very big. General relativity was still not, it was kind of an out in the boonies type field.
Yes.
But okay, so we're triangulating these surfaces. It is charming that you've been triangulating surfaces all your life. I find that some things that I did when I was like those kinds of ages are also what I've been doing all my life. But did you ever end up actually building architectural structures and things?
No, I had a little company that was going to build garages and pool covers and things like that out of geodesic domes, stretched. But luckily, nobody actually employed me.
So wait a minute, a pool cover, why is a geodesic dome? Why is a dome a good pool cover?
It's not.
I see, okay, fair enough.
It's not a good pool cover. Anyway.
But so I'm curious, how did you get the kind of entrepreneurial, started? I mean, how old? You like 16 or something at this point? Is that,
yeah,
the
15, 16. I had no entrepreneurial talent or interest, but my father said, if you're going to be a dropout, you got to get a job. You got to get some kind of job. My father was an engineer. And so since I wasn't able to find a job, I invented this company, but I have no entrepreneurial instincts. Anyway, what was very lucky was that the architecture had gotten me into a college, which was a very innovative college that had just been founded 2 years before, Hampshire College.
Oh, yeah. Right.
And when I decided I wanted to do physics, I didn't know anything about it. I took one class. My mother was a professor of playwriting at the University of Cincinnati, so I could take free classes. So I took a graduate course in general relativity from Paul Esposito, which was my first physics class. And I got some of the basics in a very primitive kind of form from him. And then I wanted to be a physicist. So I didn't know anything from anything. So I got the course catalog from MIT. A friend of my parents lent it to me. And I just went through there and wrote down all the courses I would want to take and tried to invent an education for myself. But meanwhile, I went back to Hampshire on the way to MIT. And I stopped there and discovered that they had hired a physicist who was Herb Bernstein, who was a great pedagogue as a theoretical physicist. I just totally lucked out. I spent the afternoon with him. And it was very clear that he could be my teacher. And that was very important because I was very undisciplined. I had lots of ideas. I could read a page of mathematics and understand it, but I couldn't prove anything. So I was way out of my practical knowledge. And Herb took me under his wing and was really, really hard on me for 3 years. And never said anything nice, always told me I was dumb and inadequate and couldn't do this stuff. So I worked really, really hard and got skills. And then I got into graduate school.
And then what, sorry?
Then I got into graduate school because I was abused so much, shall we say.
But so I'm curious, when Hampshire College was that young, I mean, it's always interesting when educational organizations that are somewhat experimental start up. They usually attract a very interesting crowd of students. How big was Hampshire College at that point? And was it in fact an interesting crowd of students?
It wasn't. It was an interesting crowd of students. I was in the third class, which was 200 students.
And how many were doing physics? I mean, were there a lot doing sort of sciencey things, or was it more liberal artsy, humanities type stuff?
No, the discovery was that it worked much better for science than anything else. That they're sort of focused on cases rather than survey knowledge, the individual instruction, so forth, worked really well in science. So there was another physicist, was John Dell, who became a relativist and went to the University of Maryland. and so forth. And we worked a lot together. And there were a couple of mathematicians who were
I
very...
think I've run across him. Yeah, right. But so, I mean, Hampshire had some kind of project-based, maybe still does have some kind of project-based strategy for learning. Is that right?
Yes.
So what was, so when you were in that, what were your projects? Were you doing a bunch of general relativity projects?
My project was to learn QED from the first book of BJ, Borkin and Drown. So that was a project. I was a joint student in philosophy. And so my philosophy projects, interestingly enough, were a paper on foundations of quantum mechanics and a paper about the mind-body problem, in which and this was purely accidental, but I basically advocated a view which is now called Russellian or something like that, monism.
What is that? What is that point of view?
That's the point of view that all matter has an inside aspect which can only be somehow, quote, experienced in an outer aspect which obeys the laws of physics. It was a cheap way to pretend to be a monist while you were a dualist. But the dualist part, the fact that you had conscious experiences in no way affected the application of the laws of physics. It's also sometimes called panpsychism. Anyway,
well, at least that's one version. Yeah, I've always, I've come to some of those ideas in a very, very different way. And yeah, it always confuses me when people say, this is the name for this set of ideas. And then it's like, yeah, it's anyway. But so, okay, so then you learned QED, you've learned philosophy, you already learned general relativity. So at that time in general relativity, people were, things like, the Kerr solution was probably 10 years old or something at that time. I mean, it was still pretty early days in terms of people's understanding of general relativity.
Yes.
And what was the state of, I mean, at that time, and the group of people working on general relativity, my impression was it was a very nice group of people, but a rather small group of people. Is that a correct impression?
Yeah, I think that's right. So I went to my first conference, my first year, and it was a relativity conference in New York City. And it happened that I met everybody. Somehow I met one person. It wasn't, as you say, that large of a group. And I met one of Roger's students, and then I met Roger, and then I met
Penrose. Is that Roger Penrose? Yeah.
Yeah, and I met the DeWitts. I met very briefly Bryce DeWitt and Steve Hawking. So it was a wonderful experience. And I met David Finkelstein, who made a tremendous impression on me. I had no idea who he was.
Do you understand David Finkelstein's work? Because I've always felt that he had just a lot of really interesting things to say. And I look at his books and I'm like, and I've talked to him a bunch of times, and it's like, this sounds interesting. And then one thing he told me, which really he said, you've got to realize that I've written about the same thing multiple times, and sometimes I don't agree with what I wrote earlier.
Yes, he had this idea. The way he expressed it to me when I met him was, I don't believe that God can understand infinity. So I don't believe that God can do calculus. God can sum and manipulate logic, but God cannot do calculus. And I just thought he was some crazy guy. He showed me Feynman's checkerboard. And years later, I was introduced to him by Lenny Susskind as the person Lenny most respected. And I just thought he was a kind of street person off this, out of the...
Oh, just because he had a long beard? No, that would be unfair.
Well, no, but he talked in this totally mystic way about how he was trying, his scientific method was to imagine he was God and try to invent the world the way God would with God's limitations. And that's the way he talked all the time. But the thing that among the things that he did was discover what a black hole was. So the Eddington-Finkelstein coordinates, which Eddington never understood, are the way to understand what a black hole is and what the causal structure is.
Right.
So
Right. It's funny that you talk about the God's eye view, because the previous coordinate system for the Schwarzschild solution and so on had been, actually was more of a God's eye view than Eddington-Finkelstein coordinates.
yes.
It's kind of funny. But so in that crowd of relativists, was John Wheeler part of that crowd, or was he not so much in that area?
Excuse me. He certainly was, but I didn't meet him then. I met him. No, I'll tell you when I met John Wheeler. When I applied to Princeton for graduate school.
Mm-hmm.
So they called me to interview me. And they gave me an appointment with John Wheeler. And on the way to the appointment, they showed me, for some reason, my folder. And I read some of the recommendations for myself. I was just standing there in the hallway with my folder, and what do you do? And somebody had written a recommendation that said that I was philosophical. And somebody had drawn a big red circle around that and said, sounds like one of Johnny's boys. And
interesting.
I ran faster than I didn't understand him. He was just these slogans. And the problem is my parents had grown up around mystics, and I knew I was negatively inclined to people who had that kind of personality structure. Oh. So I didn't understand what was interesting about John Wheeler till many years later. I went to Harvard. Something else I intuited was that nobody understood very much about quantum gravity, but these gauge field people really understood something about an interesting class of theories and with the standard model. So I went to Harvard to be with the people who had invented the standard model, even though they had no interest in quantum gravity, and they told me so.
Right. But so I'm curious, just coming back to something you said there. I mean, you said your parents were involved with mystics and so on. What kind of, with some particular brand of mysticism and things, or?
The Gurdjieff work, it's called.
The which?
Gurdjieff work. And it's no shame if you've never heard of it. They were a very small group led by a guy from Russian Armenia in the first half of the 20th century. But they influenced a small number of filmmakers and dancers and writers and so forth. And we can talk about it another time.
All right, that's a different, but okay. So mysticism, and you'd had experience with mysticism, which most people don't usually get. And so when you ran into physicists like David Finkelstein, who had that vibe, that wasn't I mean, I'm curious, what was Buckminster Fuller's vibe? Was he like a practical architect, or was he more of a kind of a mystical type person?
No, he was this very American type of, we can do it. We can just go out in the world and fix things. So his story was that his life was failing and he lost his job and he had no education because he dropped out of college. And he was very sad and took a walk by the river in Chicago. And all of a sudden, the thought came to him that if his life was otherwise not worth anything, he could see how much he could make it an experiment and see how much one person could do to improve life for people. Wow. So that was his motto. He just went around inventing things which he thought would be an important part of relieving poverty and attacking environmental problems and things like that.
But so, he kept on using this weird Dymaxion brand and things, but how did he get into geodesic domes? How did he get into that kind of geometry type thing?
And he had, I don't really know. I mean, I've looked at his geometry book. It's all handmade. I mean, he made it up all himself. I think he had a brilliance of being able to work that way. But, and he was the worst poet in the universe. He actually published some books of poetry about progress and so forth. And anyway,
so back to you in the when was it? Must have been mid-70s, mid-1970s or something by this point?
I started graduate school in 76.
Okay. So which was right at the time when there was, 1973 was when asymptotic freedom was discovered. That must have been all the rage at Harvard and so on at that time.
Yeah, exactly.
But so, and who did you work with at Harvard?
Well, I didn't work with anybody, but I was under the supervision of Stanley Deser, who of course was one of the great people in quantum gravity.
So he's the D for ADM formalism, is that right?
And Sidney Coleman was my extensive advisor, although he delegated everything to Stanley. And there were great people there, were undoubtedly great people. Steve Weinberg was there, Shelley Glashow. Tufts taught there for a year. People came through like Sasha Polyakov and Ken Wilson. And there were young people there who were also very good among the postdocs, who were a little bit older than me, but I could learn a lot from. So it was a great environment. And I just took the attitude that I'm going to steal as much of this technology as I can to use it to try to make a quantum theory of gravity.
Uh-huh.
And since that was new, so the idea of applying it to quantum gravity that was new, I kind of lucked out in the sense that there was this wide open range that was not that I could start to fill. So I made a lattice theory of quantum gravity, which wasn't a great theory of quantum gravity, but it was a candidate. That was my first paper.
But so was that a time when Ken Wilson was really pushing the lattice gauge theory thing? Was it kind of a Wilson gauge theory-ish type approach, or something different?
Yes. Wilson, and I had been very influenced. Sasha Polyakov came by and gave a talk, and also Ken Wilson's talk. Those two talks tremendously fired me up.
But so when you try and put gravity on a lattice in that way, does it have the same kinds of issues that it has when you try and do Feynman diagrams and things? Or does it, why haven't we heard of lattice? Usually when people talk about sort of simulations of quantum gravity, it's with triangulations and so on, more dynamical triangulations, not just put it on a lattice. What goes wrong with that?
This is a hypercubic lattice, and I used the McDowell-Mansuri action, which was particularly adapted to that. The structure of the lattice breaks all the gauge symmetries.
I see. Okay.
Which I didn't understand at the time I wrote that paper, but shortly after I finished the paper, I started to think about Hamiltonian methods, and then I realized that the whole thing I done was very, very naive. Also, I met Bryce DeWitt at a summer school, and talking with him for a few hours, I understood that I had not put in correctly the breaking of the diffeomorphisms or the ghosts generated and so forth.
But so at that time, people like Steve Weinberg, Steve Weinberg had written his book about gravitation and cosmology. He'd been involved a bit in early universe stuff. I don't think he cared about quantum gravity. I don't think he ever, I don't remember, like in his gravitation and cosmology book, I don't think he even mentioned quantum gravity, maybe as a couple of pages of discussion or something. Is that right?
He did have an important idea about that same time. I think he published in 78, which is now called asymptotic safety. He had the idea that the theory was perturbatively not renormalizable, but there would be fixed points of the renormalization group, which would be off of the 0 point, where the Gaussian fixed point is. And you could define the theory in terms of tuning it to a surface which went into the critical point. Uh-huh. And he published that in something like 78. And I think the next year, it was when I was still at Harvard, but I didn't publish it so quickly. I used a 1/n expansion to try to isolate the possibility of that non-trivial critical point. So that was
So that was like 1 over n in the matter fields, or 1 over n in some sort of generalized gravity or something?
it was 1 over n in the matter fields, and it was enough to uncover the basic difficulty with those theories, which I think has never been addressed, which is that there is an asymptotically safe theory, which is also renormalizable, which is the r plus lambda plus Gauss tensor squared plus r scalar squared. That's perturbatively normalizable, and it has a non-trivial fixed point, and it lacks unitarity and doesn't work at all. It's a fake.
How does it manage to, how do you even set up a theory that doesn't have unitarity?
Oh, you sneak. You write it in the Euclidean formulation, and then you say, let's pretend about how the singularities in the plane are going to move around when you go back to Lorentzian.
I see. Okay, so you were, at this point, you'd done sort of a lattice approach, you tried to do a 1 over n approach. This is like, and what was, I mean, is that story for you at that time, try different methods to try and see whether there's a way to get a theory of quantum gravity, and a bunch of different methods, or what was the trajectory?
Yeah, so the trajectory was, I had a number of other things I worked on. I got interested in the other side of the problem, which was the semi-classical Hawking radiation, under radiation, and so forth. And I was very interested in that. This is sort of in the 2-3 years after graduate school. And I wrote a paper about those issues, which I actually think is my best paper. Very few people have read it. But
what is that paper? Tell us about that paper.
I'll come back to it because it will take us far afield. Let me take the narration and then we'll go back to that. But it anyway got me acquainted with that whole side of the subject, which being educated by particle physicists who didn't know anything about quantum gravity, I wasn't going to get. This is sort of starting in my postdoc years. And then there were theories with propagating torsion and non-metricity and all sorts of complicated. I did the dumb thing that people do when they don't know what else to do, which is to study the complications of the problem you understand rather than the simplifications of it. And I played around with supersymmetry and supergravity. Some of this was with John Dell. But then something interesting happened, which is that string theory was invented. Well, it was not invented.
It had been invented a lot earlier. It was reinvented.
It was reinvented. And a lot of my friends and people I knew jumped into this. And I looked at it and said, that doesn't make any sense. And what we call background independence, it was not background independent. It was very background dependent. And so I started with a mathematician friend, Lewis Crane, to start to try to make a background independent approach to string theory. And most of this was never published, but we spent a couple of years on and off trying to do that. And so and this comes from Wilson and the Polyakov and all their methods on loops. So the idea was to write, Polyakov's idea was always to express QCD as a field theory on the functionals of loops, which he imagined were the holonomies of the SU3 or SU2 connection.
So is that, I mean, should one think about that if one's doing fluid dynamics? Is that like writing fluid dynamics in terms of vorticity and things like that? Is that kind of an analogy?
Yes. So my original approach to lattice gauge theory had, and which I was interested in, and some of these other things we played with, was the idea that the metric and the connection were independent variables. And therefore I saw ways to study operators based on loops of electric or magnetic flux with the gravitational field. And with Lewis, we were developing the algebras of such operators and trying to use them as a basis for string theory, non-perturbatively. So that didn't work, but then Abai Ashtekar invented, it's not really true, somebody else invented, Abai Kassan invented, but Abai developed to the extreme this approach based on the chiral connection. And all the tools that Lewis and I had developed were just sort of ready to attack that idea, Abai's idea.
But so to try to understand, I mean, so this is, for example, in your idea for string theory, this was a different set of degrees of freedom, a different sort of coordinate system for strings, which would instead of a string propagating on a background, it would be intrinsic representation of the string in terms of some kind of loop variables. Was that kind of the idea?
Yes.
And was that something? What I mean. And there would be some Lagrangian or something for this intrinsic loop thing. And was it expected to be a field theory, or this was a quantum mechanics, or this was a classical?
A field theory, no, quantum field theory, but on a space of loops.
So then when you see the famous, Pantz diagrams or something for strings, your idea was that what you would be representing was those loops joining and so on directly. Is that kind of the notion?
Yes.
So does that work in the end? I mean, has somebody actually done that now, or is that still unpublished?
I think that loop quantum gravity does construct that representation where the states are functionals of loops and graphs and so forth. We can come to it. There are things it does, in my opinion, and things it doesn't do. But
so back to the beginnings of loop quantum gravity. So this is what year now? This is like mid 1980s or something, or what? What's that?
1986. Abai published his paper on the classical formulation of this in December of 85. And immediately I'm working on it. I'm trying to get some friends together to work on it by putting in the kind of technical toolkit that we had from studying the
So can you just describe so what do you now see as having been the core idea of that paper?
The paper we wrote.
No, the Ashtekar paper. I mean,
the idea of the Ashtekar paper was completely classical. It was, let me say it, I mean, he went at it in a very insane, terror-inducing way. Let me say just what's true, the easiest way, which was a few papers forward from that. And this, in some sense, is a paper of Ted Jacobson and I. But take the action for general relativity and write it in what's called the Fabansky form. I'm sorry, the Palatini form, which is to write it separately as a function of the connection and the metric. And then when you vary the connection, its field equations give you back that the connection is actually the metric connection, the Christoffel symbol.
So hold on a second. I mean, the normal, normally it's R squared of G is, the standard Einstein-Hilbert action. So you could take that R and write it out in terms of a bunch of Christoffel symbols and things, or what is this? I've heard of this Palatini action, but I have to admit I don't remember what it is.
So the basic idea is that whereas Hilbert and Einstein wrote the action as a function of the metric, where when there occurred a connection, they put in the Christoffel symbol as a function of derivatives of the metric.
Okay.
Instead, you have the metric and the connection as independent fields. So there are additional field equations, and they turn out to be the equations that say that the connection is the Christoffel connection made from the metric, plus some other pieces. And the other pieces will help you to do things like couple to fermions.
So let me just understand that. So I mean, the naive way of thinking about differential geometry is the metric sort of is telling you everything, and you should be able to derive from the metric the connection, the Christoffel symbols, the curvature, et cetera, et cetera, et cetera. But so this is now a different, this is saying, let's consider the Christoffel symbols as dynamical variables on their own. Is
Yes.
that the...
Yes. Yes.
And so it is a different physical theory. It's a theory where, I mean, so just to give an analogy, in gauge field theory, you would have the analog of the Christoffel symbols is the gauge fields.
Yes.
And so normally, and in, you know, in standard gauge field theory, you know, gluons and things like that are thought to be things in themselves.
Yes.
What's the, I mean, in gravity, well, so what's the analogy there? I mean, so is this, how is that a different, what will be the theory that is like Einstein-Hilbert for gauge field theory? And then what is this different kind of thing where the Christoffel symbols are dynamical degrees of freedom?
Well, we to hold that question for 5 minutes. So I have to do through 2 more steps.
Okay.
First of all, we're going to, if you want to couple to fermions, we decompose the metric into frame fields. This is just another way of expressing the information in the metric. You give at each point 4 fields which are orthogonal, 4 vectors which are orthogonal according to the metric. And that's a different way to code the metric. And just
what's that called? Is that this Vierbein? What is that? What is that?
That's the Vierbein. That's a frame field. Now, now look at the action, and it's got terms like this E wedge, the curvature tensor R, which is again the curvature tensor just of the connection field. So it looks just like a Yang-Mills theory with E wedge, the Yang-Mills field strength. And then you can write E to the 4th, and that's really the cosmological term, and so on. And now I want you to do something really crazy, which is, if you know something about, which I'm sure you do, the structure of the Lorentz group, you can write it as double cover as SL2C, and that you can break up into 2 commuting pieces, a left-handed piece, which gives the chiral rotations of left-handed neutrinos, and a right-handed piece. And they commute with each other. So I want you to...
for massless neutrinos, right? And I mean, that requires...
Yes.
Like,
So, and I want you to cut that action in half, and you'll see that it is separately a term in the left-handed chiral connection, that SU2 group, which acts only on left-handed fermions, and another plus another function, which is its canonical conjugate of right-handed connections that couple to right-handed fermions. And then the following is what Ted Jacobson and I had discovered, which was so weird, and then we'll get to a by, is cross out one of those terms. And then you've got a complex action for complex variables. And it turns out that that's still the Einstein equation. That is, if you're willing to insist on real functions being real, so you complete everything that's left-handed by adding its complex conjugate, you only need half the fields, the left half of the fields. Moreover, I'm going to have you do one more thing, and then I'm going to tell you why the result is fabulous. The frame fields always exist, turns out, in the action in a structure called E wedge E, which is a 2 form, which has its own chirality. Its complex conjugate is its chiral other half. So we want you to write, to every place there's an E wedge E, write a B, which is this left-handed two-form, left-handed self-tool two-form. And we want you to write the action as a function of the left-handed connection in these B's. And the first thing that shocks you is that you have to put in a kind of Lagrange multiplier field to make it work. And its field equations say you build the B's back from the E wedge E's. So you just have the B's, the connection, and the matter, and this Lagrange multiplier field. And that equation, which I can write for you in a minute, is purely cubic and the simplest possible thing that you can write. So whereas the Einstein equations, normally are infinite order and you have to expand and evaluate 1 over the determinant of the metric and the square root of that, this is an equation written in terms of forms, which is the action is purely cubic and the field equations are purely quadratic. So there are many advantages if we're going to try to make that a quantum theory.
So hold on a second. I'm just trying to understand the intuition behind this. I mean, it feels very wrong to take something and say, I'm only going to consider the left chiral components or something.
Yes.
It feels like you've only got, you'd only have left circularly polarized gravitational waves or some weird thing like that.
Yes.
What is the physical interpretation of saying you only, I mean, is it that the, I mean, or it would be like in fluid dynamics saying, I'm only going to consider vortices that go in one direction. But maybe the degrees of freedom of space-time are enough that only considering the vortices in one direction, you can kind of turn it around and look from the other side and it all works okay. How should one think about that?
Taking the complex conjugate to define the real versions of the metric is more powerful. All the complication is expressed, or a lot of complication is expressed in a statement of what's a real field.
So I see. So by forcing it to be real, you are effectively adding back the degrees of freedom that you took out when you said, I'm only going to consider the left chiral component or something.
Yeah.
I mean, it's like in when you do quantum field theory, you would always write, here's the Lagrangian plus Hermitian conjugate. Is that kind of the thing that you're doing in this case?
Yes. Yes. But
okay, but so the remarkable thing that you're saying, which I have to admit I didn't know, so is that when you write things in terms of these variables, what was a determinant and a square root and so on becomes a pure polynomial in those variables.
And a low order polynomial.
Okay. And it is a mathematical identity that that low order polynomial thing in terms of those variables is equivalent to the standard Einstein-Hilbert action.
Yes. Yes.
And there are no like boundary terms or something where you're effectively doing integration by parts or something or
there are, and the boundary conditions are beautiful because the boundary conditions that you have to add to that structure are exactly true in Simon theories of the connection on the back on the connection pulled back into the boundary. So we can make use of a lot of structure and a lot that people know about quantum Chern-Simons theory. So that's very helpful. There's another thing you can say about that action, which is I said there's a term where we use a Lagrange multiplier to make a field equation on the B's whose solution is that there exist A's, E's, the frame fields, which are such that B is E wedge E. So if you don't introduce that equation, then you have a theory which is just a function of the B's and the A's, and no E's ever occur. And that's a very interesting theory in its own right. It's a topological field theory, so it can be used to measure the topology of manifolds. And it's something that we can write the partition function for in its exact form, since there are not local degrees of freedom. And there's a lot known about that. And then what we're telling you is general relativity is a projection of that path integral that insists on those conditions so that ease exists.
But so what is the physical interpretation of Lagrange multipliers?
The physical interpretation is you have a path integral, which is in some sense trivial, or at least exactly expressible. And we want you to go into the measure of that path integral and remove some terms from the sums.
Mm-hmm.
And then it's no longer topological field theory, but it is a candidate for an action for general relativity. And then one can bring in lots of tools that you wouldn't have known about to understand it.
Fair enough. But so you say it's a candidate for an action for general relativity, so it is no longer something which is mathematically sort of equivalent to, I mean, because of what when you do that mathematical derivation from Einstein-Hilbert to, you know, decomposing it in terms of these other degrees of freedom and so on, where is the place where you're having to make assumptions that are essentially physical assumptions?
Well, in the classical theory, it's fine. I mean, the assumption I didn't tell you about is that you have to make sure you get to Einstein's theory, you have to assume that these frame fields and these B fields are non-degenerate. Otherwise, they'll produce you solutions that don't have enough structure to reproduce general relativity, as well as the solutions for general relativity. For the quantum theory, it's
Sorry, what does non-degenerate mean?
The determinant of these B fields are not zero.
And what's the physical interpretation of that?
The structure is breaking down in a way that may be interesting, but isn't a theory of metrics. So
when they're degenerate like that, you can't produce a metric from it. Somehow the volume has gone to zero or something, or what's the...
Exactly. The volume has gone to zero. We know the outcome for the volume. And so now you have a functional integral. The functional integrals there are many heuristic, beautiful things about functional integrals, but if you really want them to be the foundation of your theory, you have to show they converge. And there is
Really? Can people show anything about path integrals? I didn't think people could show very much mathematically about path integrals at the best of times.
Yes, I agree with you.
Okay.
And the state of the art is some formal results and then a number of numerical results, which have the natural mathematical language here is the representation theory of groups. That is, you can put everything that involves functionally integrating over gauge fields into functionally integrating over a dual, which is representations. I think that's called the Peter-Weil theorem or something like that. That if you have a harmonic analysis on the space of connections which converges, you can convert the basis where the states are functions of a connection for a basis where states are functions of polynomials, basically.
Okay. So that's a loop story again. That's going from the underlying differential geometry to some kind of loop representation.
Right, which has these wonderful, among the few things that are straightforward and simple to compute are things like the operators which measure the energy, the area of faces, and these turn out to have computable spectra.
So wait a minute, would the area of a face would normally be like in Reggie calculus or something? What is the physical interpretation of the area of a face?
So you have to define the face.
Yeah.
So let's say we're going to we're talking about the Hilbert space in the neighborhood of a black hole, and we're going to use the horizon of the black hole as the space as the the thing we hold on to when we define some observables. So one of the observables we can define is the area of the horizon, and implement that on these Hilbert spaces. And it has a discrete spectrum, which we can compute with some work.
But so that spectrum, I mean, involves things like H bar and so on, presumably. I mean, where does that come into this whole? I mean, this is a path integral where the weighting of the path integral is the standard quantum field theory e to the I times the action weighting type thing. Is that the idea? But so actually now I'm curious. I'm sorry. You said you could explain later what you think, what your best ever paper about Hawking radiation and so on is. So since you've mentioned black holes, we have to ask again about that. What was that paper?
Oh, the main idea in that paper was that when people did semi-classical relativity and computed the Unruh effect or variations of it, or the Hawking effect, they always made the following assumption. There are classical physics, there are special frames of reference which are inertial frames. And in quantum field theory, there are special frames of reference which are minimal radiation frames.
Yes. And
they assumed that they were the same. And that's where how all the results were generated. That's how you tied the vacuum of the quantum field theory to particular asymptotic regions or surfaces of symmetry. But these all were assumptions. And so I wanted to play a kind of equivalence principle game and see how much I could argue from just those as stated as assumptions, as sort of kind of find an expression for Mach's principle.
Well, it's interesting. So I mean, just to recap, I mean, the basic idea, you have creation operators or something that represent the presence of, the things that create particles, and in the presence of a background, curvature in the background space-time, the form of those creation operators changes. But the assumption is that at infinity, when you're far enough away from sort of all of the black hole stuff that's going on, that those that the creation operators for the quantum field agree with the creation operators for the quantum field in a standard flat vacuum. Is that right?
Yeah. And my point was that everybody just assumes that's true, but we should come out and make a principle of it.
Because the principle is that the asymptotic states that in some sense sufficiently far away from what's going on that the vacuum is the vacuum, so to speak.
Yes.
And how does that, so in Mach's principle, I mean, so now I'm curious. I mean, like if you have a rotating setup or something, which was the kind of the place where, what on earth happens to that idea of sufficiently far out, everything is just the ordinary vacuum?
The rotating case is hard and doesn't follow the usual expectations.
Okay.
If you remember Dennis Sciama and...
I knew Dennis well, yes.
Yes, he worried a lot about things like this.
Mm-hmm. But okay, so your result was, your idea was, have it be a principle that quantum fields sufficiently, what was the idea? Quantum fields sufficiently far away from curvature or something will actually be the ordinary quantum fields, or what was the analog of the equivalence principle?
It's embarrassing not to remember your own paper, let alone your own best paper. But
was it something like that you could always because the equivalence principle would say you can always substitute with acceleration and so on. You could always put a different gravitational field there, and maybe you would have a principle that would say you can get sort of an arbitrary deformation of the quantum field with a gravitational field. Is that it?
Yeah, but that's not the way I stated it. The way I stated it was there are two techniques to locate some preferred frames or preferred states of motion. One of them is where we measure accelerations. We follow Galileo in his ship in Venice, and we look at the birds flying and the bees rushing around, and we figure out what the inertial frame is.
Wait a minute, I don't know that story about Galileo. What is that story?
Oh,
sounds like a story.
that's in his Two New Sciences. There's
Oh, yeah?
a beautiful, beautiful paragraph in which he introduces the principle of inertia and does it right and does it very beautifully. So,
But and it talks about gondolas in Venice or something, or?
well, being in a ship and going below decks so that you couldn't see
Ah.
how the ship was moving.
Okay, so that's where Galilean invariance came from. I didn't know that.
Yeah, it's a beautiful passage. And so, and I said there's another way to find a preferred set of frames, which is measure the energy produced by your frame.
Like the particle production, like how much particle production there is.
Yes. And the principle was that these two frames should coincide to leading order, because the equivalent principle is a leading order statement.
So wait a minute. So you're saying, that's an interesting idea. So you're saying, look at the particle content. Instead of saying, I've got an accelerating frame, it's got a weird particle content, say, use the particle content as the way to decide it's inertial or something like inertial if there is no particle content in it. Is that the?
Yes, but then the idea is that we say, oh, wow, they're the same frames up to curvature effects. And that was the principle, that they should be the same frame.
That's interesting. Okay. Yeah, that sounds like an intuitively useful principle, but okay.
So let's go. Should I finish the other story?
Yes, please. The loop quantum gravity story, because that's the, yeah, right.
So the loop quantum gravity story, let me just editorialize a little bit. My sense is that there's a lot of it which is very elegant, which presents an interesting picture of how we might think about quantum space and time. There's a toolkit which is rather wonderful, and one of the things that I endlessly don't understand is why, I mean, there are lots of people who go around saying loop quantum gravity is inadequate, and that's fine, and we should make another theory. But they should steal our toolkit. We have a great toolkit.
Yeah, I think several people working on our project are trying to do exactly that. So
that's all. But my sense is that, and I have friends who get very angry at me when I say this, but I think actually something is basically what I think of string theory, what I think of dynamical triangulations, what I think of causal sets. These different approaches, they have beautiful features which explain why some people are enthusiastic about them. And they have persistent problems, which no matter what you do, you don't get by, and which are worrying. So I think, unfortunately, none of the things on the table are plausible to me candidates for the quantum theory of gravity. They may be plausible for describing some limits or some corners of regimes.
yeah.
But we don't have the whole thing yet.
The thing that I found exciting is I've only known kind of a layperson's knowledge of all these different approaches to quantum gravity, right? And so, in our efforts to pursue sort of our lower level machine code kind of thing, I had no expectation that it would connect with any of these existing areas. What turns out to be the case is it seems to connect with all of them. Well, I can say more accurately, causal set theory, definitely. Causal dynamical triangulations, definitely. Loop quantum gravity, don't know yet. That would be, I think it will be the case. Spin networks, almost certainly. String theory, not so clear, but probably. But, what seems to happen is that, in something like causal sets, it's like, the original causal set theory is just throw down a bunch of events in random places. What we have is sort of an algorithmic way to generate where those events should be. And that means that you can use all the technology of causal set theory, which says, given that you have a distribution of events, here's what happens. but now we have a way to explain why the events should be that way. And I would sort of suspect that the same kind of connection would exist with loop quantum gravity, except I certainly don't understand loop quantum gravity well enough to be able to see that. But that's some and that's, I think it's I certainly didn't see this particular direction emerging of there's all this technology that's been produced. And by the way, what seems to be the case, and again, my currently perhaps naive point of view, the machine code that we have seems to connect to all of these approaches. That is, it's not saying, oh, causal sets was right, dynamical triangulations was wrong, spin networks was whatever. It seems to be that all of them end up being, different descriptions, different degrees of freedom, so to speak, and unable to describe what is ultimately the same kind of thing. So which is kind of neat, because it could have been the case that some group of people were just off working on something that just made absolutely no sense and had no foundation, but I don't think that's the case. It sounds like you have the same prejudice.
I have the same belief, and what I also think is an opportunity once we see things that way is that we can understand what are the limits where string theory begins to talk to us, and what are the limits where these other areas begin to talk to us. And first of all, that suggests a lot of physics to think about. Second of all, you realize there are some limits that are unexplored. And so there's work to do, which is organized by that.
Right. Well, I certainly have some ideas about that. But I'm curious, when you look at loop quantum gravity, if you were going to say, I mean, like for us, for the models that we have, there is a somewhat definite way one could imagine making a sort of space-time microscope, a gravitational microscope, so to speak, where one can, like in fluid dynamics, usually we're looking at, continuum fluids, but there are experiments we can do where we can see the molecular dynamics. So similarly, we can sort of we have ideas at least about what kinds of experiments you might do that would see through to the molecular dynamics of space-time, so to speak. And I'm curious, in loop quantum gravity, what would be the type of thing that you would expect to see where, okay, at some level, yeah, I mean, if like for example, for a fluid, one might have, okay, so an analogy might be, Kolmogorov's theory of turbulence, where everything is represented in terms of eddies, and you have this whole cascade of eddies going down to small scales and so on. Should one think of, is there a situation, a very kind of bizarre and naive question perhaps, but I've always wondered, is there an analogy to turbulence in gravity?
Yes.
And if you think about it in terms of, it sounds like you're thinking about things almost in terms of eddies. Do you have intuition about that?
That's really good questions. I don't have much intuition, mostly because I don't know much about fluid dynamics or turbulence. But there is a lot that's interesting about that, and I also don't think it's hard to see what loop quantum gravity needs. So I just say it's just a few things. What are the persistent issues we have? One of them is, if you think about it, almost everything we know is at the limit of small g h bar. Let's keep C fixed. So g h bar gives the Planck area, which is why we have all these areas and volumes which we can measure at the Planck scale. So we control quantities that are in units of powers of gh bar, but g over h bar, or rather h bar over g, is where the energy lies. So in other words, by looking only at quantities in gh bar, we can talk about geometry, but we can't talk about dynamics. There's no place to write a Hamiltonian which comes out in units of gh bar.
Wait a minute, naive question, because I don't know the dimensions of G properly. What are the dimensions of gh bar? Is it a length or something?
It's a length squared.
Okay. So that's a Planck area-like thing.
Yes, but we don't really have nice statements for the energy of what we imagine is that dynamics consists of local moves on those triangulations, on those discrete structures. And we know a lot about some asymptotic forms of those local moves, so we can write partition functions and dominant contributions, partition functions and so forth. But we can't really honestly talk about energy as something which is happening in the theory. So I think that's a huge issue.
Well, so just to understand, the I mean, in traditional, I mean, is the theory initially a theory of pure gravity? There's no matter in the theory originally. Is that correct?
That doesn't. I prefer to have matter all the time, but that's
okay. But so usually energy. I mean, obviously, the energy momentum tensor has a contribution from matter fields. It has a contribution from gravitational fields. Usually, is when you say there isn't energy in the theory. Is that, I mean, usually you can at least say that there's a bunch of T mu that comes from the gravitational field. Is that not something that can be done in this case?
Not easily.
I see. Okay.
There are a few special cases where energies end up related to areas. For example, if you're in the frame of reference of an observer held just above the horizon of a black hole, then you see in action a Hamiltonian, which has a term in the area of that horizon. And that's been used by Eugenia Bianchi and Alexandro Perez and a few other people. But mostly, let me just list this, mostly the technologies that I think we want have to do with computing energy. And it's how energy evolves dynamically. So I think we've got a corner of something. We've neglected things in powers of h bar over g. Related to that, classical general relativity has a positive energy theorem. And that's very important for the physics of gravity. And it's not of the form of the integral of something positive over manifold. The energy is very implicit in general relativity. But we have no access to that quantum mechanically. We don't have, to my knowledge, we don't have a way of stating a positive energy theorem.
So, it might be helpful in our kind of theory, right? You've got these hypergraphs that represent the structure of space, and they have this evolution that's based on rewriting of hypergraphs and so on. In our models, one of the surprises is that energy there's a very simple interpretation of energy. If you look at the causal graph of the, of update events in this hypergraph, and you look at the causal edges in that causal graph, then energy is simply the flux of causal edges through space-like hypersurfaces. The interpretation of that is effectively, it's roughly measuring the amount of activity in this network. So I would be curious, I mean, in what you're describing, so just to understand the dynamics, I mean, you have these essentially discrete loops, but your dynamics is what is the dynamics? What is there an interpretation of it in terms of some kind of discrete process, or is it just you're saying this is the partition function, this is the path integral or whatever, and then it's traditional kind of, doing a path integral type thing?
No, so here's what we know about the path integral. Imagine that we describe everything in terms of four-dimensional triangulations. Mm-hmm. So that means that we have a lot of four simplices around, tied together in different ways, filling up a four-dimensional volume.
So this is like Reggie calculus, or like something like that, yes?
Yes, and the boundaries of these four simplices are three-dimensional geometries. Mm-hmm. And they are typically triangulated by tetrahedra. Mm-hmm. And we do a path integral over all the ways to connect these things up, plus the areas of the surfaces, and that's all from the geometry side.
Mm-hmm. But
And
that, I mean, but that kind of thing, like spin networks and things like that, that's a kind of a way of giving a measure on the space of possible configurations. That's not as such a dynamics. I mean, like in our kind of models, there's a definite dynamics. It's just time evolves and something happens at every step in time.
Yeah, so now that I didn't tell you the dynamics. So the dynamics for a particular dynamics is push forward that quantum geometry, three-dimensional geometry, by putting four simplices down at places wherever you like, because we're going to do a path integral. So we're going to sum over all the ways to build a four-dimensional manifold by putting four simplices down and labeling when you have space-like tetrahedra, they attach to other space-like tetrahedra, and being careful about the not changing locally the signature. And each time you add a four simplex, you multiply by a certain factor, which I can tell you what it is. There's the 10J symbol, which represents an intertwined.
Right. 10J, I know about 9J. I don't know about 10J.
Okay, so the 10J, I think I can get this right. Maybe I mean the 9J, but we'll see. We have we have a four simplex. A four simplex has 5 tetrahedron in it, 10 surfaces, 10 dual surfaces, and that should add up to the degrees. I'm starting to fail because the 10 that I'm interested in are the 10 dual faces, which give the edges of the dual triangle.
Okay.
And we pile these up, and we're going to sum over the values of the lengths of the dual triangulation and the volumes using this. We also have an operator at the vertices where 5 tetrahedra come together, which measures space-time volume.
Mm-hmm. So one thing I'm curious about, just to understand the sort of intellectual landscape. So there are spin networks. There's the thing you're describing. So I mean, spin networks grow out of quantum mechanics and grow out of the theory of combining angular momentum and so on. What you're describing is how do you see the analogy between what you're talking about and the spin network idea?
Well, so the spin network idea, the three-dimensional states are described by spin networks.
Okay.
SU2 spin networks, to be precise.
Mm-hmm.
And that sums you over all different geometries, assuming certain things about the topology, which are stuck together. When we put in the four simplices, we are putting in eigenstates of the Lorentzian geometry. And the representations there are actually the representations of SL2C. And so there are these infinite dimensional representations. And so what we're summing over, in some sense, we're holding the SU2 spins on the boundaries fixed, and we're summing over the SL2C spins that meet the boundary. And we have a particular condition which relates the representations of SU2 the representations of SL2C. And
so naively, wait a minute. I mean, naively, because there are, I mean, you can index representations of the rotation group by just discrete indices, the J's and so on. For you know, in the Poincare group, right? There's momentum P, which is not quantized in the same way and not bounded. There's not quantized in the same way. Is what you're saying that there's a continuous degree of freedom associated? There's some other continuous degree of freedom that is not some discrete, you know, group, you know, thing that's like a you know, a compactly group representation thing. Is that kind of the idea?
yes, exactly. So let me tell you this, because I've only recently really understood this, because when I was going somewhere else when all my friends were doing this. But SL2C is not a compact group. It's Lorentz group.
Mm-hmm.
And the physics, if we want it to be Lorentz invariant, we have to respect this structure. And when we're building force simplices using representations, the same way that we build a spin network using representations and give that the dual geometry. So a 4-valent node in a spin network is dual to a tetrahedron and so forth.
Mm-hmm.
If we want to represent space-time, we need to have physics Lorentz invariant, and we therefore need the unitary representations of the Lorentz group, which are infinite dimensional, and they're labeled by continuous, by real numbers or complex.
Which are essentially momenta, yes? Is that right?
Yes. But
Okay.
there's a long way in that essentially. And then here's something that I find very beautiful. In both the cases, I said that if you leave off the certain constraints, you got a topological field theory in both the Euclidean and the Lorentzian case. And I argued that if we're going to impose these constraints that turned you from the topological field theory into general relativity, the place to impose them is the measure in the path integral, the measure of summing over all these things. So the functions I put in there are functions that if you sum over everything, because of the recursion relations of 10J and 6J singles, the recursion relations just show you that there's no dependence on anything apart from the boundaries.
Okay.
What the theory asks you to do to make general relativity a theory with local degrees of freedom is not touch anything but the representation summed over. In the Euclidean case, the representations are labeled by J left and J right, and you sum over all of them with no relation between them. That's like saying that the theory breaks down totally into a left-handed bunch of sums, and a right-handed bunch of sums. Barrett and Crane said, if you add the condition that you're only going to choose the representations so that J left is equal to J right, that's general relativity. And then you have to make an argument. Okay. In the Lorentzian case, the corresponding statement is a little bit more interesting. So let me say where it comes from and then say how it's projected. And then that would probably be enough. So in sort of thinking about quantum gravity, we think a lot about boosts and areas, because boosts and areas together define these chiral subgroups of the Lorentz group. Mm-hmm. Basically, the left-handed fields are those where you're boosting as you're making a left-handed rotation, and the anti-self-through ones are the ones where you make a right-handed rotation while you boost. And so those are, those each define representations. Now, what we want you to do is choose a representation such that there's a relationship between the left-handed representation and the right-handed representation that reflects in a simple way, and there's several lines of algebra, but reflects the fact that we're summing either over the left chiral rotations or the right chiral rotations, but nothing else. In other words, out of the possible members of the Lorentz group one could sum over, we're restricting ourselves to those.
Right.
And now let me something, and that we claim gives general relativity. And now let me say something very cute, and then I'll shut up because it's part of the saturation for many of us, certainly for me. When you say that the left-handed constraint tells you that there's a certain amount of boost, say in the Z direction, which is related to a certain amount of rotation.
Oh, you really have picked up Canadian. Sorry, excuse me. Z is a
yes.
Yeah. Go ahead.
I'm around the right axis. So you take the Z axis and you're interested in representations where it's constant how much you boost when how much you rotate.
Mm-hmm.
But it's not hard when you, so we want to impose that as a constraint. And let me just do a little interpretation. The rotation is related to the spatial SU2. And this is, their representations are associated to areas. So we really have an operator here that says there's an area. You're on some surface in space-time, and we're measuring an area, and the area is proportional to a boost. Now, there's a constant of proportionality that I forgot to tell you about that we snuck in there, which is called the emergence parameter. So let's just sneak it in there. So the area is related to this parameter times a certain amount of boost. But the boost is a boost in energy. So what that really is a boost. What we really mean by a boost is a Hamiltonian which generates boosts. So we're saying a measurement of the area over here is like measuring the boost energy with some parameters and setting them equal to each other, at least in the expectation value. But the boost energy, if we think of the Unruh effect, the boost Hamiltonian is related to the acceleration times the regular Hamiltonian. And when you work all that out, and I'm now cutting some corners, you have a statement of the first law of thermodynamics. That is, if you assign entropy to the area that you defined here,
yeah, I get it.
And energy, boosted energy crossing the horizon with some parameters put in here, this geometrical statement becomes the first law of thermodynamics.
By the first law, as in energy conservation.
Yes, yes.
But so you're saying that, okay, so in your interpretation, energy, you're saying that this area, there is an the area is essentially generated by boosts that correspond to energy. That is that as you look at the forward evolution of areas, if you look at the space-like hypersurfaces, that somehow the successive states of these little elementary areas are the things that are produced by essentially these little tiny boosts. Is that kind of the idea?
Yeah, so I'm saying the TDS, so if we use the fact that the area is related to the entropy, then there's something in a change in the areas, a change in the entropy.
Yeah.
Is related to an energy input.
I get the idea, but I mean, what you're effectively saying there, if I understand correctly, is you're thinking you've got these space-like surfaces which are sort of triangulated, and then what you're saying is to generate the next space-like hypersurface, you are thinking about that as something like a sort of an elementary boost of one of these areas. Is that right?
Yes.
So I mean, that's quite charmingly related to, I mean, in our kind of setup, basically you have this hypergraph, and at every moment, what's happening is pieces of that hypergraph are being rewritten. So it's not the same, it's not represented in the same kind of way as you're talking about. It's not represented in terms of loops and things. It's represented, I mean, we usually think about it in terms of pure, well, I guess hyperedges. I bet there's somebody who's on this Zoom here who probably understands this much better than me. But I mean, for us, you can think about kind of time evolution is the consumption of hyperedges turning into other hyperedges. Mm-hmm. For you, it sounds like time evolution is the turning of one elementary area into another elementary area. Is that right?
Yes.
Oh, that's interesting. Well, that's interesting. That's very that's very nice. So in your setup, your notion of the progress of time is, I mean, because usually in path integrals and usually in sort of space-time formulations of things, time doesn't have a particularly special status. Mm-hmm. In your setup, does time end up having a pretty special status, or it's some?
Let me confess and separate two things. I've been giving a schematic of how loop quantum gravity could recover known physics. Mm-hmm. And basically, the name of what I was doing is there's a beautiful paper in 1995 by Ted Jacobson, where he relates the laws of thermodynamics to the Einstein equations. And I'm claiming that observation is built into the geometry that we learned was in the interesting evolution law for these spin-foam states. And that generates a certain attitude towards time and so forth. And I'm happy to talk about that. But I should put a warning that my own views on time have run much ahead of that and are more radical and maybe
we should talk about that for a few minutes, because just since, I mean, I have very definite views of time that have kind of emerged from my adventures, and I don't know whether, I mean, you know, for me, kind of the primary thing about time is this kind of inexorable process of computation that is sort of an irreducible process, and that is kind of the measure of something having been achieved by the progress of time. And I'm curious, what do you think, you know, how do you think about time? What do you think time is, so to speak?
Well, so this is remarkable. It's almost, it's somewhat the same thing, but without the words about computation. But maybe if you force us to the wall, we'll admit to thinking about computation. So this is, the two people I've worked most with this are Marina Cortez and Khalil Verde. And the picture is that the world is always in process of being built. We're not interested in what exists, we're interested in what happens. And what happens, we see in an ontology of events. And what an event is, so the only observers we are interested in is observers inside the universe. We're not interested in external observers. And for us, an observer is an event or is some generalized event. And what is an event? An event is a place where a number of quanta coming from the past, or even define that as where they come from as the past, meeting and making a decision about setting some quanta onward to the future.
Yes.
And what
we
happens?
We call those things token event graphs. That's our name for that term. Yes.
Beautiful. And when we think about how those processes happen, some things which are originally indefinite become definite in the process of an event. For example, if an event, and this is part, well, let me just say it. If I am at an event, or I am an event here, and I want to think about an event in the future, that is, the states of possible children or grandchildren of mine, then I use Hilbert space and quantum states, because the future is indefinite. If I'm describing my past, I just use an ordinary description, because we know what the past was. We have the best possible to.
You need to be introduced to multi-way systems. They are a very beautiful way to think about the kinds of things you're talking about, and they make it a lot less. Okay, but now I want to hear about your way of thinking about it. Yes.
Well, so interestingly enough, this evolved over a long set of conversations with Talia Verde, and one of the things we discovered is that if you dig enough into the history of quantum mechanics, a lot of people are saying things, well, Schrödinger, Heisenberg, Freeman Dyson most eloquently, a number of other interesting people are saying this. Bragg says the future is quantum and the past is classical. And Heisenberg says the quantum description, the Hilbert space description.
Okay, that's different. That's not, I mean, that way of describing things is not similar to things that we've described, at least not so far as I can see. But I'm curious. I mean, okay, I'm skeptical about that being the right way to think about it. But so your concept is that, I mean, for us, we can make these graphs that have, we've got events going on, they consume certain inputs, they generate certain outputs. Yeah. And I don't know what, well, okay, so if we think about that kind of graph, which it sounds like you're also thinking about, what is the difference between that graph? I mean, that graph seems like it's essentially a time symmetrical thing. What's the, where does the kind of difference between past and future come in that kind of interpretation?
It's subtle, and sometimes I get confused about it. But because I've tried to think about the past, the one that would be symmetric in past and future. But let me put that aside, because I haven't made that work the way I would want it to. So in the asymmetric...
Let me maybe make a comment about that, because that's the old story of the second law of thermodynamics. Basically, is how do you deal with the fact that, and what I've come to understand, I mean, I finally understood this sometime in the 1990s. I thought about it for ages. The key thing about what is a plausible observer, the main thing you have to do to explain the difference between past and future in thermodynamics is to understand that you can't set up some initial state that is a bizarrely constructed thing so that it will show anti-thermodynamic behavior. Such an initial state is not realistically constructible. Similarly, for the observer isn't a Maxwell's demon-like thing that is noticing all these micro details of molecules. The observer is just noticing certain kinds of coarse aspects of the structure. And I think, the thing that I've kind of understood is that when you think about the process of evolution as a computation, this business about what observers have to do they have to outrun the computation in the system itself. So they have to essentially do very sophisticated computations to be able to set up that correct initial condition. And if you assume that the observer is computationally bounded, that's not something they can do. And that's why you observe thermodynamic behavior and so on. So I'm curious, when you made a statement that you think of events as being like observers, I don't think of that. I think of observers as being things that make equivalence classes of events, that coarsely make equivalence classes of events, and that the individual events themselves are way below the level of something that an observer is sensitive to. So I'm curious if you have a different point of view about that.
I've thought, no, not developed. What we've been struggling with is something like, so let me back up. If we have a causal structure, we have an event in the causal structure, it has a causal past.
Yep.
And the recent causal past can be represented as related to things which are true at the event. So I think of an event, just the mathematical formalism I like to use now, is a two-sphere with some punctures. And the punctures are where a light-like quanta arrived at the celestial sphere.
You need to draw some causal graphs. Yes, okay, fair enough. You've basically got a graph, and you're thinking of representing that graph in terms of sort of an embedding of that graph in which there's a two-sphere around every node of the graph, and you're looking at where the graph edges poke through the two-sphere.
Yes.
Is that right?
And the job of, so first of all, I want to say that quote, what's real, because like John Bell, I want to say what's real. What's real is the information about its past that every observer has, that every event, has. It has some unambiguous knowledge represented by punctures and labels on the two-sphere about its recent past. And I want to say that those are real.
So I find that very bizarre for several reasons, okay? So in my way of thinking about things, and I suspect also in your way of thinking about things in terms of these, the loop quantum gravity approach, what's in a sense real is just the connectivity graph. The embedding of that graph and saying, what lat long of the two-sphere this particular edge is going through is not something that I would expect to be I would expect to be that to be some kind of gauge choicey type thing, not something that is any real feature of the physics of what's going on. But are you saying that the actual geometry, the latitude, longitude, saying this causal edge went through at, 30 degrees north, 16 degrees west or something, that matters in what's going on?
It's a representation.
Okay, but does it, yeah, I mean, there may be a concrete representation, like when I do a graph, when I draw a graph, I generate a graph in, Wolfram language, and it renders in some notebook somewhere, and it's going to render in a particular form with particular, with the nodes laid out in particular places. But I don't imagine that layout, beyond being useful for me as a human understanding what's going on in that graph, I don't imagine that layout to be significant. But okay, so you're saying you are caring about that graph embedding. It matters to you what the actual layout of the edges is.
Yes.
Okay.
And I'm positing that's what's real is for all the events, the collection of those two spheres with labels on them. And that I call the views of every event has a view. And
so for me, for us, it would be, there's an event, it has a past light cone. That past light cone is a big chunk of causal graph.
yes.
Which is, a chunk of causal graph that is defined by a graph, basically. That's just a piece of graph. We don't say what the embedding of that graph is. we just know that that graph has certain connectivity. But you're saying, in addition to the graph structure, you say there's also an embedding that you care about, an embedding in 3+1 dimensional space-time.
I don't care about the embedding.
Okay.
I've said something misleading. I don't care about the embedding.
Okay, fair enough. But so you are really, so you're saying the past history of this event is defined, and I would certainly agree with this, is defined by the causal graph, by the past light cone, by the causal graph that lives in that past light cone.
Yes.
Okay.
And every event has to make a decision, which is to make a partition of the energy that's been given it and send some quanta forward at some particular angles with some distribution of the energy and momentum that's been given it.
I understand. It's like a scattering event. It's kind of like in particle physics, it would be a scattering event right. Yeah, I mean, I think in our models, it isn't as complicated as that. In our models, there isn't a serious scattering amplitude. In our models, what we say is that there are a certain set of events that can happen, and all of them happen. And so, and all of them happen in different branches of this multi-way graph, and they correspond to different possible histories of the universe. And so, in other words, rather than saying of a given event, let's look at the micro probabilities for that individual event, we're saying, well, where you're saying, look at each event. And as I understand it, you're saying, look at each event. And for that particular event, it has a certain scattering amplitude, and that event has certain probabilities of putting quanta out in these directions and those directions.
Yes.
And so what we're saying is, so in a sense, that will be kind of like a mean field theory of what we're talking about. Because what we're talking about is to say, there are certain events that are possible. We will essentially generate out this multi-way graph, as we call it, of all possible such configurations of events. And we could represent that, at least approximately, by saying each event has certain probabilities. But what we're actually saying is we're looking at all possible, this really giant computational structure that is the sequence of all possible sequences of events, so to speak. But okay, so what you're saying is you're looking, it's a sort of probabilistic theory where at each event, at each elementary event, there is and your representation of the world is in terms of these quanta. That's actually surprisingly close to what we're talking about, because for us, every causal edge represents a certain, the flux of a causal edge through a space-like surface represents one unit of elementary energy. So in fact, in that sense, for us, causal edges are energy. I mean, which I think is the same as what you're saying. I mean, so I think for you, perhaps, for us, the flux of a causal edge is a flux of energy. Whereas I think you're saying, perhaps, maybe you're saying the same thing, because you're saying that at one of your events, do you have some energy conservation principle at the events?
Yeah. Yes.
Okay. So that's, I mean, for us, it's a little bit more complicated, because what we're saying is that the flux of causal edges through a space-like hypersurface represents energy, but knowing what the density of that, for a flux, you have to have a density, you have to have some kind of area measure, and that's a slightly complicated thing to work out. And that requires kind of thinking about general relativity and so on. But okay, so then, okay, so in that model, you have essentially a Boltzmann-like molecular chaos story about what's past and what's future.
Yes.
That is, so what I was saying about the preparation of the initial state is important. If you could prepare an initial, I mean, how do you imagine that the initial states are being prepared?
I don't imagine. That's very interesting.
Okay, fair enough. I mean, so but your model should have a Boltzmann equation, basically. Your model should have an equilibrium configuration, right? If what you have is quanta coming in, quanta going out, that's just like, that's just like the standard setup for the Boltzmann equation.
It's a gas.
What's that?
It's a gas.
Yeah, right. But, and by the way, it's not self-evident that the gas limit would work. I mean, that's something you'd have to establish, right? I mean, it could be, does it matter? Because the whole assumption of a gas is that the outgoing quanta, as you're calling them, are uncorrelated. I mean,
Right.
that's essentially the, and if the thing is actually a liquid or a solid, that's not true. I mean, that's not a good approximation. So why do you think, I mean, it's actually an interesting question. Why do you think that space-time viewed in this way is more like a gas than a liquid? And is it the case, perhaps, that in some extreme situations of high curvature and so on, that in your picture, it wouldn't be the right thing to think about it as a gas rather than a liquid?
Yes, and what's happening here is that we've gone into the part of the theory that's not completely developed and not published. So my answers are getting vaguer. Right?
What's that?
My answers are getting vaguer.
That's fair. Yeah, right. No, I mean, but to me, I mean, it is interesting that the intuition that you seem to have. I mean, I think your intuition is fairly similar to what we're talking about, except that our model is simpler, much simpler. I mean, it is simpler in conception, but considerably more complicated in actually working out its consequences. Although the good news is that because we can leverage all this technology that's been built in causal sets, in higher category theory, et cetera, we've actually made really good progress in untangling what the consequences actually are, which is kind of nice.
Yes, that is. Can I tell you the one trick that we found, which might be worth something for you? So, the causal set program has a problem showing the emergence of a classical space-time in which it embeds, in which its histories embed.
Yeah, I think Jonathan Gorard, who's been working on our project, wrote this paper about algorithmic causal sets, which I think the causal set people feel is a pretty big step forward in untangling that issue. So I suspect you may have a similar way of untangling that issue.
We have a very easy way to untangle that issue, which I'm surprised other people haven't noticed. So there's Nether's theorem. And Nether's theorem says if you have a uniform direction in space, there's a corresponding conservation law. Mm-hmm. But there's an inverse Nether's theorem. And it goes something like this. If you have a dynamics of momenta, so everything I've been saying is there isn't an embedding in space, but these objects are carrying definite units of energy and momentum. So there's a combinatorial framework on which you've pasted, there's no embedding in space-time, but you've pasted copies of momentum space at the different events. And you have ways of transferring energy and momentum among the different events. Mm-hmm. And you enforce a conservation law. Now, here's a little trick. A conservation law is going to be a delta function in your partition function. It will be a delta function of the conservation law. And you can write that as introduce Lagrange multiplier Z, and let's write that as the integral over Z of EDI Z dot the conservation law. Mm-hmm. That gets all these Z's into your path integral. And these Z's live in the inverse of momentum space. And basically you can show that if you can solve all those conservation laws, then each conservation law is like a little piece of a Minkowski space-time with a few events on it. And if you can solve all of the equations thus generated, then basically you tie yourself together. Those little fragments tie into a Minkowski space of the same dimension of your momentum space. So it's a kind of simple way to make sure that you generate a big Minkowskian space. This is basically the inverse of Nether's theorem.
Yeah, I understand. I mean, but what you're saying is, I mean, usually when people do in causal sets, they do, you know, Poissonian sprinkling of events. And what you're saying, I think, there is that there is there's some kind of phase fluid of events, and there is some kind of conservation law about the phase fluid of events forces a Minkowskian structure. Is that kind of the?
And you can see it in our papers. It's quite explicit.
That's nice. That's nice. I mean, so essentially what you're saying is that corners of the Poisson sprinkling should not be reached because, in fact, there's essentially a phase fluid of events that just wouldn't be able to extend in that direction.
Yes.
It's interesting stuff. We are probably running out of time, which is a shame because this has been a lot of interesting things discussed. I am curious to ask one question about kind of the structure of science, okay, which is the whole, you know, you were involved in the founding of the Perimeter Institute, is that right? Or were you its first director, or?
No, I was the first director.
But you were kind of, what was the, I just don't know the history, and it's what caused the Perimeter Institute to exist? I mean, was a large part of it related to science that you've done, or did it have some independent reason to?
The story is, Stephen, the story is really interesting. And it's not what you would expect. What caused Perimeter Institute to be done is Michael Lazaridis having invented the BlackBerry and finding himself very, very wealthy compared to anything that he could understand, decided to become a supporter of science. He was a dropout of engineering school. And so our founding story is that and he was one of two individuals who were essential. The other one was just finishing a PhD in theoretical physics and deciding, this was Howard Burton, deciding that he wanted to leave academic science. And so he sent CVs to a number of places, including Research in Motion, saying, give me something interesting to do. I know I could go work on Wall Street or Bay Street and make a good living, but can you give me something interesting to do that uses what I know? And Mike picked up the phone and called him and said, we're happy to interview you at Research in Motion, but if you're really crazy, meet me tonight at dinner at such and such a diner, and I've got something to show you. And Mike unfolded this vision of making a scientific institute. And you have to understand, neither of them knew what they were doing. Howard, at least, is about to get a PhD, but he's never run anything.
Who is this person? Who is the? Say again.
Howard Burton. You've never heard of him. Nobody's ever heard of him. But for some reason, he was exactly the right person. So as they talked, Mike offered him the job of basically the first director, and which is insane. And you can appreciate how
I think it's great. It's yeah, okay.
And Howard said, I have to think about it. Mike said, take the weekend to think about it, because if you say yes, this is the last free weekend you'll have in several years. And Howard, all this was in Toronto. Howard went to, there's a boardwalk called the Beaches the next day, and thought for a few hours and sat down and wrote Mike an email, which was the conception of the Institute, the scientific focus, the organization, even the name, the strategy to make this, etc. It was like in a 10-page email. And somehow Howard was exactly the right person.
What was his PhD about? What was Howard's PhD about?
Quantum gravity.
Who had he worked with?
Paul Brabman, who's at the University of Waterloo.
Okay. So he was interested in quantum gravity. So was he an enthusiast of your work, or did he have a particular sort of direction of quantum gravity that he was interested in?
No, well, yes and no. For somehow, and I don't know why he was so smart, but one of the principles that he enunciated at the beginning is one of friendly competition. If you're going to go into, it's not worth going to any area that's not capable of giving rise to a breakthrough. If you go into an area where you're going to try and make a breakthrough, you hire a number of people on different sides of the controversies and issues, and you make sure that everybody feels simultaneously paid attention to and supported and completely insecure, because there's no mandate that says that there's going to be quantum gravity of a certain type here. Everything is on the table. Everything has to be demonstrated. We don't have any fake parameters here. By progress, we mean real progress. By breakthrough, we mean real breakthrough. And so that's why we have string theorists and quantum information people looking at quantum gravity, and us. None of us who come from the quote quantum gravity world still work completely in it, and so forth. And the idea was to set up a sort of camp of friendly opposition.
So what was Mike, who I've never met, we've exchanged email, but I've never met him. So he's run a business for a long time. Yeah. And I know a little bit about running businesses too. And there's certain kinds of things one thinks about, like what are the objectives? How do we figure out, what project are we trying to achieve? So when Perimeter Institute was set up, was there some similar kind of, there is an objective, this is what the objective is? Or was it more, we're just going to make this melting pot where there are different scientists doing different things?
I think that Mike he had several objectives. One is, which he did not directly impose, but it was imposed in some of the first hiring. And so we had, for better or worse, an advisory committee. And this was that there is a breakthrough to be made in quantum foundations, in quantum mechanics, that will lead to new technology. And this was always his mantra. He would say, it doesn't justify it, we just want to do the pure science. But as a businessman and as somebody who thinks about the future of industry in Canada, we don't have enough innovation. We need a breakthrough, which is native here.
But quantum gravity wouldn't be, for me, it's like, it's a few hundred years to go from, I would have thought, actually, I now realize that I'm wrong about that, but I had thought, from quantum gravity to technology is a few hundred years, not a few years, so to speak. Yeah. What was
no, but Mike's point was, you don't want a few years. If it's a few years thing, then industry can support it itself, because you can justify an investment in it. So Mike wanted to say, what are the furthest, deepest problems? And let's get the best people and give them everything they need to focus on. So
his original concept was, and it's been quite, I think, from what my impression, I've never visited Perimeter, I've never had never been in the right place at the right time, so to speak. But my impression is that as a kind of piece of regional development, so to speak, it's been pretty successful. In terms of defining of economic development and so on. But so that was part of the plan from the beginning, so to speak. It wasn't kind of, let's just go and do this thing that is sort of reaching for the stars, so to speak, of figuring out a quantum theory of gravity. It was more, let's do something that will bring technology and innovation to Canada. Is that right?
Bring is a funny word. He wanted to shame the politicians.
Okay, because he says he didn't like the base support for basic science in Canada.
Yes. And
Did that work?
It put us in a very difficult position for the best of reasons, which is that we were so much better resourced than anybody in physics in Canada that we came under a lot of skepticism and envy. Especially you give the job of directing this thing to a kid who has no experience. So
what happened to that kid? That kid must not be a kid anymore. What's happened to him now?
Well, that's a sort of sad story, but you'll probably, well, I'll be interested in your comment on it. The kid, it was amazing. He was smart. He, as we opened, we had a sort of double system, which very few people understood. One of them is that, of course, all decisions are seconded by the board. And the director reports to the board and proposes, which is the way that the natural way that you would do this kind of thing. I now understand that I didn't understand. I learned a lot. I didn't understand that then. Within the walls of the Institute, we had a very open democracy with no hierarchy and lots of stuff that was sort of a radical experiment in academic self-governance.
Why does this remind me of Hampshire College somehow? Was this a recreation of the, I don't know.
And I was the one who was very interested in structure. Like, I went to Oxford and Cambridge and I talked to the old guys who knew what the rules really were. Because, all these places are self-governing and they function on constitutions that are 500 years old. And
like, you mean the Oxford and Cambridge colleges and things?
Yeah.
Do they actually have constitutions? I didn't know they had them.
King's College, for example, has a constitution.
Oh, how interesting.
And so we ran by consensus for a few years, but there was this secret, which is that in the end, it was Howard's judgment. Now, there was an advisory committee that went to the advisory committee of the board. Now, Howard was smart enough to figure out that after only a year or two, that he was smart enough to actually hire good academics, because people are really simple-minded. That is, we had all these fancy advisory committee people, and they would sit there at our great expense and say, what you really want to do is hire very good people. And at some point, you figure out that that's true, and what it means that that's true. So there were a lot of things that Howard did well, and a lot of good decisions were made early, and it grew very fast and flourished. Now, Howard made a mistake. So he and Mike were very close and ate breakfast together once or twice a week. And Mike was not that much older than Howard. So it went very well. And we really did develop an atmosphere of cooperation in which the different areas we tried to support each other in doing the best. And we were very careful and slow about hiring. So we did a lot of things right, and it was going well. One of the issues was, of course, tenure. Mike was against tenure, Howard was against tenure, I was against tenure.
But so there were a bunch of people, like probably you, who quit tenured jobs to go work there.
Well, there were three of us, Raymond, Rob Myers, and myself.
Mm-hmm.
And what we discovered is that you can trade tenure for being a founder, because there's no experience like that. But
you can also have the confidence that, if all failed, you could go back and get another professor job. If you don't have that confidence, it's kind of a bad sign.
I don't know if I had that confidence or not, or cared. but it was clear to me an opportunity of a lifetime.
Mm-hmm.
And but it doesn't work years down the line. Years down the line, you can't offer somebody the experience of being a founder. And then tenure was always decisive. So our science advisory committee pushed strongly on the board, and at some point tenure was added, sorry.
That's a financially complex thing.
Oh my God. No, and I look at it, and I mean, I'm not on the finance committee, but I can add. And there's the standard thing to worry about, and which is you adopt. I didn't think we should have tenure. If we had tenure, I thought we should make it very restrictive to a small proportion of the faculty, because what happens is we now have 20 of our own faculty. Then there are some borrowed, mixed, etc. cases, but let's talk about the pure cases. And 16 of us have tenure, and there's sort of 4 who are going to get tenure pretty soon. And that's it. And we're well paid, and we're expensive, and we're hard to get rid of. And it's a real issue. And
but I don't understand the finances of that, because if you live long and never retire, presumably there is a fixed endowment for the organization. And
yeah.
How does that work? I mean, in other words, you would be that seems like a very complicated thing.
Yes, and it is, and let's come back to that. Let me tell you the story of what happened to Howard, because he made a mistake. This is my point of view. I mean, Howard is a friend of mine. This is not what he says happened, but this is what I observed, and it has to do with politics. And I don't know how much you know about Canadian politics.
Almost nothing, but
okay.
Go ahead.
It's somewhat analogous to British politics.
That doesn't help me much, but yeah, go on. I can guess, but please go on.
Anyway, Perimeter was the project, clearly something so another thing that was explained to Mike by Howard and other people who got on the board is you don't just say, I want to found an institute and put $100-something million in a bank account and let it run until the bank account dries out, which was actually his original vision. Mm-hmm. What you do is you go to governments and you say, I'll put this in if you put that in. Mm-hmm. And so a deal which was sort of 1-to-1-to-1 of federal funding, provincial funding, and private funding, where the private funding mostly came from endowment, was established. And this is a thing that people who knew enough to do it set up at the very beginning, and was an important thing. And anyway, we were tied to the Liberal Party, which is sort of something like, well, anyway, it's the center-left party, and was in power then. And the finance minister who shepherded us through became the prime minister for a few years. And there was an election coming up. His name was Paul Martin, and they were going to lose, and it was going to be taken over by the Conservatives. And so here's the story. Mike comes to Howard and says, can you advise me? Paul Martin is coming to Toronto. He's going to announce a number of science innovation projects. He wants to use our stage to do that. And among that is going to be a $50 million addition to our funding from the feds. And in exchange for that, he wants me on the platform next to him while he's making these announcements. And Howard says to Mike, don't do it, because that government is going to lose, and it will look like you're nailing Fermina's fortune to the dying ship of the liberal elections. And it looks scummy. The whole thing looks like a desperate attempt to buy votes. So Mike said, but there's loyalty, and I have loyalty in the room. So he went and stood next to Paul Martin, not at Perimeter, as it turned out, but somewhere else. Simultaneously, Howard published an op-ed in the Toronto newspaper saying, I am the director of Perimeter Institute, and I would like to thank Paul Martin for this pledge of support. But this is a cheap, crazy political act, which is desperate given the fact that they're all about to lose.
Yipes.
And as the director of Perimeter Institute, I can't just let this go by. So my view is that that's when Howard lost his job.
What did Howard have a political axe to grind as well? Or did he just, I mean, did he have an actual opinion between these politicians and things?
Surely he was liberal, but he was apparently already in contact with the leading people in the Conservative Party. And
why did he think it was important to stick his neck out on this issue?
Because he had an agreement from the Liberals to give the same $50 million if he stood independent. Because he had a deal with the Conservatives.
So in other words, he wrote that op-ed as part of sort of tipping the scale against the Liberals somehow.
Yes.
I see. So he got kind of pulled into the swirl of the politics of the whole thing.
Yes, and he thought he could keep it controlled.
Sorry, he thought what?
He thought he could keep it under control. And no, it was fantastic because a week or so after that, I'm in the building. His secretary calls me and says, there's a gentleman so-and-so in the building. He came here to have a meeting with Howard, and he has an hour free. I had met him somewhere on something for better education, and he wants to meet you for tea. So, and I don't remember this guy's name, but he was the mentor to the person who was about to become prime minister. And he was meeting there already with Howard 2 weeks before the election to negotiate how the Conservatives would embrace the project of Tenure.
Did they in the end?
Yes.
I see. But they're kind of, and so why did Howard, who had, done this slightly peculiar sticking his neck out thing on behalf of those politicians, did they get him ousted for some reason? Or what was the dynamic?
I think, well, what happened is that the new prime minister came to announce his science and technology budget at Perimeter after the election, after he was prime minister. And we had a prime minister reception for this. And Howard spoke on the stage and introduced everybody. And 5 minutes after the prime minister left the building, the vice chair of the board marched Howard up to his office and fired him.
And so what was the political, what was the board heavily entangled with the politics, with the country politics?
Yeah, but first of all, Mike felt betrayed. Mike felt stabbed in the back. This is all my reconstruction.
Yeah, right. So I'm curious, when Mike was Mike involved with the science of Perimeter, or was he mostly kind of the global vision of do something important in physics? Was he actually, does he understand loop contragravity and things? Is that the level of involvement?
He's smart, He's a good engineer. He used to hang around a lot, but no. And he knew enough to understand setting up tensions. And so he set up an advisory committee, which from my point of view had too much influence, but they were very good people. So before he hired, well, me, Rob, we were two of the first three hired. He had spent a lot of time with Chris Isham, Roger Penrose, etc. And Howard had set up all these meetings so that, and Mike is, he's sometimes wrong in my opinion, but he's a very good judge of character.
So why did he pick quantum and quantum gravity and things like that? Why was that? I mean, it's not the most obvious thing for a telecom-oriented engineer to get excited about.
Oh, no, it is, because, well, first of all, quantum gravity is the coolest thing, but he already knew about quantum information and quantum computers. And Raymond was our third hire. And when we hired Raymond, we understood that that should really be a separate institute for quantum computing. And that was put at the University of Waterloo. We were never actually at the University of Waterloo. We're completely independent, which is very important.
So do you think in the end that Mike has been happy? I mean, it's been what, how long has it been, 20 years or something that they, has this, is it, you know, it's always a thing I'm curious about when people spend some chunk of their fortune on some, you know, intellectual kind of thing. In the end, are they excited about it? Or are they like, oh, those intellectuals went off, those academics went off and did something kind of random and didn't really do much for me? What's it?
No, I think he's very proud of it. And I see him for lunch or dinner once or twice a year. So we're not friends, but we keep up. Let me mention the counter case, because Mike was a co-CEO, which was one of the things that doomed perimeter research in motion. And his co-CEO was
Don Badel something or other.
Yeah, Basili.
Okay.
Who was a Harvard Business School graduate and so forth. And Basili wanted also to make an institute. And it's across the street from us. It's in, it's in political theory and social sciences and so forth.
I had no idea. What's it called?
The Basili School for International Relations.
Okay.
And roughly speaking, it's a disaster. That is, Basili, what Mike knew about leadership and how to set up something, Jim never understood at all. And Jim set up a school, and there was some institutes connected with it, in which there were never the best people appointed in roles of governance. There was a lot of parking of Canadian intellectuals who needed work. There was much closer connection with the politics of the country. And
the subject matter sounds like it lends itself to that. I mean, quantum gravity is not usually a political platform.
Yes, but it just, I mean, they have also a beautiful building, although I think not quite as good as ours, but you know, an architectural building which, like us, got a medal, and I forget, Queens.
Does your building have geodesic domes in it by any chance, or did not manage to? Was quantum gravity not enough in the mind of the architect to end up with triangulations?
They played with it. But it's not. There's a whole history to that also. Anyway, what was interesting is that there have been some good students who came, a handful of good students, to my knowledge, who came out of the Basili School, but it was a tremendous waste of resources. And the good faculty that they managed to hire left, got acrimonious and left.
That's
And
interesting.
it is interesting. And Mike never, at least to me, came and said, I think you should hire X rather than Y. Except when it was the case of the director. When it was, as chair of the board, it was his direct responsibility to hire a new director.
But so, I mean, is the main thing that Mike has been pleased about the fact that he's managed to bring innovation to Canada? Or is it more the kind of, oh, we got this particular science result and, his funding was responsible for that happening?
I don't know. You'd have to ask him. I mean, what he's doing now, he's disconnected from us. He's disconnected from Research in Motion. And he does basically venture capital in quantum technologies.
I see. But so that's interesting. So I mean, is Perimeter now sort of, it's a government-funded, self-sufficient kind of thing, or it's living off it? It's invested its endowment and it's living off the investment.
Oh, I don't know.
So do they let the scientists be involved in the investment, or is there some completely separate investment group that is figuring that stuff out? I always think it's interesting at universities that have elaborate economics departments and finance departments and so on. Do they let those people mess with the endowment or not?
It certainly would not be good to let me mess with it. There is a investment chair, investment subgroup of the board of directors, and they are no matter how esteemed our people are, they are principally retired CEOs and so forth of the major banks of Canada. So they pick on for that.
Oh, it's interesting. We have gone way beyond the time that we had said we would go. So but this has been quite fascinating, and
let's keep talking, and we come as soon as I can invite a visitor.
Right, I've never been to Perimeter. It's been one of those someday. So your building doesn't have geodesic domes, but it does have award-winning architecture of some kind.
Yes, and it's great. We have two buildings. The original one, in my opinion, was a great building.
Okay, and that's the young Lee who might have been an architect speaking on that in that. Interesting.
The first architecture by Gilles and Perot. Gilles and Perot. They were a Quebec team. Anyway, come and see it and see what you think.
All right. Okay. Sounds like a good thing. And and you should drop in if you're in Boston sometime.
I hope to travel again.
Right. We'll see what happens in the world. The funny thing for me is that because I've been a remote CEO for, now it's 31, 32 years, that this whole everybody doing everything remotely was like, okay, now everybody's doing the same thing I've already been doing. So I felt kind of guilty. For how little effect it's had. All right, we should wrap up. I see a very nice comment here on our chat from David Chester saying, thanking you, Lee, and describing you as the architect of reality. That's a good tagline.
That's a beautiful thing, and it's very flattering, and it's not true.
That's nice. All right, we should wrap up. So very, very nice to chat, and thank you very much, Lee.
Great. See you very soon.